Hello everyone, welcome back to the channel. Today we're diving deep into one of the most fascinating areas of aerospace engineering, the heart of modern fighter jets, bombers, and advanced aircraft, their engines. Specifically, we're comparing the jet propulsion technologies of the United States and Russia. These two countries have been pushing the limits of aeronautical performance for decades, each with its own philosophy, engineering style, and military doctrine. While their aircraft are often the ones in the spotlight, the engines inside them are what truly determine speed, agility, range, and survivability. So, let's break down what makes each side unique, from the exterior to the core performance, safety features, unique selling points, and of course, how much these engineering marvels cost. When looking at the exterior of US jet engines, one thing stands out immediately: precision manufacturing and a focus on stealth integration. US engines, like the Pratt & Whitney F-135 used in the F-35 Lightning II, or the General Electric F-110 in the F-16 Fighting Falcon, are often designed to blend seamlessly with the aircraft's fuselage, minimizing radar signatures. The nozzles are engineered with serrated edges or variable geometry to both reduce infrared visibility and optimize thrust vectoring. The exterior often looks clean and compact, with minimal protrusions. This isn't just for aesthetics, it's for aerodynamic efficiency and stealth effectiveness. On the Russian side, engines like the Saturn AL-41F1 for the Su-57 or the AL-31F for the Su-27 family often feature larger, more rugged external profiles. Their nozzles sometimes have a more cylindrical or flared appearance, and while stealth shaping is becoming more common in newer Russian designs, traditional focus has been on raw thrust and durability over radar evasion. Russian exterior design often emphasizes easy field maintenance, meaning more visible bolts, access panels, and even reinforced structures that can handle less than ideal airfield conditions. Moving to the interior, US engines are packed with advanced materials and high-tech manufacturing methods. Single crystal turbine blades, ceramic matrix composites, and sophisticated cooling channels are standard features, allowing US engines to operate at extremely high temperatures without degrading too quickly. The internal layout is often optimized for modular maintenance. Technicians can swap components with minimal disruption to surrounding systems. In contrast, Russian engines tend to be slightly less reliant on exotic materials but are renowned for being overbuilt and forgiving. The internal design prioritizes robustness, meaning they can operate in dust, cold, or heat with less concern for perfect environmental control. They may not always match US engines in terms of material science sophistication, but they excel in practicality and resilience. Performance is where both countries truly shine, but in different ways. US engines often lead in terms of thrust-to-weight ratio and fuel efficiency. The F-135, for example, produces up to 43,000 pounds of thrust with afterburner while maintaining exceptional reliability over long maintenance cycles. These engines are often optimized for sustained supersonic speeds, better acceleration, and superior range. This is partly due to extremely tight engineering tolerances and advanced digital engine control systems that adjust fuel flow, turbine blade angles, and nozzle position in real time. Russian engines, on the other hand, may not always match US designs in efficiency, but they often produce explosive bursts of thrust that give aircraft incredible climb rates and maneuverability, especially in short bursts. Engines like the AL-41F1, capable of producing around 32,000 pounds of thrust, allow fighters like the Su-57 to perform high-alpha maneuvers and super-maneuverable tricks that impress at airshows and can be deadly in close-range combat. Russian design philosophy accepts shorter maintenance intervals in exchange for raw power output when needed. Safety features in US engines focus heavily on predictive maintenance and digital monitoring. Full Authority Digital Engine Control (FADEC) systems constantly monitor every aspect of engine health, warning pilots and ground crews of potential failures before they happen. US military doctrine prioritizes keeping jets in the air for long missions with minimal risk of mechanical failure. Engine fire suppression systems, containment rings to prevent turbine blade debris from damaging the fuselage, and redundant fuel supply systems are common. In Russia, safety features are approached with a different philosophy. While modern Russian engines are catching up with digital monitoring, historically they relied more on structural over-engineering to survive damage. This means an engine might keep running even after ingesting debris or sustaining partial damage. Russian safety also comes from the ability to quickly repair engines in the field without waiting for specialized tools or climate-controlled hangars. Unique selling points for U.S. engines start with stealth integration and fuel efficiency. The ability to maintain supersonic speeds without afterburner, known as supercruise, is a hallmark of some U.S. fighters, like the F-22 Raptor with its Pratt & Whitney F-119 engines. Another major selling point is longevity. U.S. engines are designed for long service lives, often exceeding thousands of hours before needing major overhauls. For Russian engines, the unique selling points are their ruggedness, ability to operate in extreme climates, and sheer thrust in certain models. They are also often less expensive to produce and can be adapted for multiple aircraft platforms with fewer changes, making them appealing to countries looking for affordable, high-performance jet power. When it comes to price, the differences are substantial. A single Pratt & Whitney F-135 engine costs around $14 million, while older but still advanced U.S. engines like the F-110 might be in the $4 to $6 million range. Russian engines like the AL-31F are significantly cheaper, often between $2 to $4 million per unit, with more advanced models like the AL-41F1 coming in around $5 to $7 million. However, these price differences also reflect differences in maintenance costs over the engine's lifespan. U.S. engines might cost more upfront but can save money in the long term due to longer intervals between overhauls. Russian engines may be cheaper initially but require more frequent maintenance and overhauls, adding to lifetime costs. In conclusion, the comparison between U.S. and Russian jet propulsion technology isn't a matter of one being definitively better than the other, it's about philosophy. U.S. engines tend to focus on efficiency, stealth, longevity, and digital sophistication, making them ideal for long-range precision missions and sustained high-speed flight. Russian engines emphasize raw power, resilience, and adaptability, making them formidable in environments where conditions are less than perfect and maintenance facilities are limited. Both approaches have proven effective in different contexts, and both continue to evolve. The real winners are the engineers pushing these technologies forward, ensuring that whether it's American precision or Russian toughness, the skies remain a proving ground for the ultimate expression of aviation power.